Hello and welcome to another episode of Reservoir Seismology, a series of videos from Sterling Seismic and Reservoir Services in which we discuss modern seismic methods that are designed specifically to be applied to reservoir engineering problems. In most cases, seismic results are combined with rock mechanics analysis to extract rock properties and reservoir condition parameters that are useful to reservoir engineers, for example, pore pressure. Thanks for joining us today, and we hope you find the information useful. Today's topic is seismic reflection imaging with DAS data for reservoir management. I'm your host, Brian Fuller. The talk outline looks like this. First, we cover the basics of DAS, which is an acronym for Distributed Acoustic Sensing. Then we look at the data acquisition with DAS in a horizontal well. And primarily, we'll be looking at data that is recorded in a horizontal well in today's episode. Next, we look at seismic velocity changes from time-lapse seismic images. And then we look at engineering applications of the DAS reflection imaging and the results that we get from the seismic velocity changes. And finally, we review the main points. This slide shows the components of a DAS seismic survey. First of all, we have a Wellbore in the red line, which starts out vertical, goes to some depth, and then turns horizontal. We have a fiber optic cable that's either inside or outside the casing of the Wellbore. We have a surface seismic source, which in this case is shown as a vibra-sized truck, but it could just as well be dynamite or some other seismic source. To the left of the surface seismic source, we have the interrogator laser system. The laser shines light down the fiber optic cable, and the interrogator measures the strain rate at every point along the wellbore, or every point along the fiber optic cable. The seismic data that's output is actually, a measurement of strain rate of the contraction and elongation along the length of the fiber as seismic waves pass the fiber. A very important point about fiber optics is that we get effectively a receiver station every few feet, like between 3 and 15 feet all the way along the fiber. This is a much, much smaller station spacing than we've ever had with seismology, and we get thousands of data channels along a fiber. For example, if we have 20,000 feet of fiber and we have a station every 10,000 feet, or every 10 feet, we end up with thousands of data channels. We've never had this level of data acquisition before in borehole seismology, and we get a great deal out of it. Here we have the sketch of a cross-sectional view of a wellbore. We have steel casing as represented by the black circle. Area inside the steel casing obviously is blue. On the outside of steel casing we have cement, and cemented in is a fiber optic rod. It's a multicolor group of circles there, and that's the way most fiber optics are actually deployed in wellbores. They're actually cemented in on the outside of casing, and it goes in as the casing goes in. Alternatively, we can deploy a retrievable fiber system, which is shown as a little group of colored dots on the inside of casing. And that can be pumped in, or it can be conveyed on, say, coiled tubing or some kind of a carbon fiber rod, as some companies do it. So we show here a diagram of the data set that we'll be showing today, the real data set. We have as blue dots going down into the earth, a wellbore going vertically down to about 9,000 feet, and then it turns horizontal. It's fairly short horizontal. It's about 4,500 feet long. At the surface of the earth, we had vibra-sized trucks. There were 96 source points at a nominal spacing of about 150 feet. And below the horizontal part of the borehole, we show a seismic reflection image. And this is the image space that we'll be showing. So it's actually below the horizontal part of the borehole. In this slide, we see the reflection image that resulted from the baseline seismic survey. That was the data was recorded actually before this well was fracked. So I want to acquaint you just a little bit here with some of the elements of the data. Again, this is a reflection image here. It's a post-act migration, FD migration. The data is in the time domain. It's in milliseconds below a flat datum. Now, the red line that we see going across the top of the seismic data, that's actually the wellbore location. And it's a slightly toe-up geometry, with the toe-up side being on the right-hand side. The flat datum is just about 4 feet above the datum, 4 feet above the toe elevation. And so again, this is two-way time relative to that flat datum. We see a bracket over on the far right side indicating that at about 55 milliseconds, we have about 325 feet of depth relative to that flat datum. The trace interval here is 6.66 feet over a total image length of about 4,155 feet. Again, this trace length, or this trace interval, is actually quite tight compared to, say, surface seismic, which is typically on the order of 100 feet. So one of the benefits, again, of the DAS and the very small station or receiver spacing we can get from DAS data is that we can get very small CDP intervals. The frequency content of the data is the maximum usable frequency is about 105 hertz in this image. The fiber size sweep maxed out at about 120 hertz. And so we can push the frequencies a little higher than that with post-stack widening, but we didn't do that in this case. Again, this was this data was recorded prior to the fracture stimulation for this well. Now the next image we'll see was after fracture stimulation and then 4 months of flowback and production. This is the reflection image that came from the first time-lapse data set. So again, this was recorded about 4 months after fracking. They put the well on flowback and of course ran into production right away after that, or continuously with that. So there are some pretty significant changes that we can see in this reflection image, and we'll show you, I'll emphasize those in the next 3 slides. These 2 red arrows indicate 2 places to look, and we'll show you the time lapse here in a second, episode 1, episode 2. But I just want to direct your eye to 2 different places where we see quite a lot of change. The first one is in this gray reflector at the top, say in the 10 to 25 milliseconds range. We see quite a lot of change in that reflector, which is not surprising since it's really close to the wellbore. And so a lot of the fracture should have occurred in that area. And then that lower red arrow is a place where we saw some really big changes in the reflection coefficient. It almost looks like there's a change in structure, which isn't the case, or can't be the case. But the reflection coefficients can change. So you'll see where those are in the next 2 slides. So just to have a visual look at how things changed between episode 1 and episode 2 of the seismic data. Here we see, again, the baseline survey prior to the frac, and now we move over to episode 2 after 4 months of after fracking and 4 months of production, and we see there are some big changes in the gray reflector, which again is where we would expect to see some big changes as it's close to the wellbore, and then also that large reflection coefficient change at about CDP or crossline 260. In this slide, we show the results of measuring the change in interval velocity from between the baseline seismic survey and the first seismic survey 4 months later in the upper 140 feet of the section just below the pipe. So with the horizontal well is that blue line at the very top, and then about 140 feet down we see another reflector, a red reflector, and we measure the percent change in interval velocity between those 2 seismic surveys. And down below we see the red curve is the percent change in interval velocity over that time frame. And there's 2 very distinct trends there. They starts at a increase in velocity, then decreasing, and then at about cross line, say 220 or 230, we see the same pattern repeat. Now, interestingly, the black curve above the red ones is oil production, and that's in barrels of oil per day that was measured, again, using a DAS cable. The DAS cable can passively listen to fluids moving into the borehole, and it can determine what kinds of fluids there. Well, it's either oil or oil and gas. There's no water produced in this field. So it's very interesting that we see an increase in production with a decrease in compressional wave velocity in 2 separate trends. We see those 2 separate trends. We see increasing production and then we see decreasing interval velocity. By the way, there's these kind of little spiky production zones, and interestingly, those are very strongly correlated with the position of the plug and perf plugs between the end of one perf stage and the beginning of the next one. So in that little short interval in between two stages where the plug and perf, the plugs for the plug and perf, between one stage and the next, so the end of one stage and the beginning of the next spatially, that's where that high production is. It's a very interesting correlation. Although it hasn't been mentioned up until now, in addition to be able to do P-wave reflection imaging, as the P-wave images that we've shown so far, we're also able to do shear wave reflection imaging, and that this is actually a time-lapse shear wave reflection image that we're seeing on the screen right now. The shear waves were generated from in a downgoing S wave conversion, so P to S downgoing conversion, and we're able to use the same virtual source technology that we use to generate the P waves to then also generate shear wave reflections. Additionally, you can see the same red and black oil production and interval velocity change curves in the shear wave here. And we're able to see here that we actually have an increase in shear wave velocity with increasing production, as opposed to the compressional wave decrease in velocity with oil production. And this has implications probably to do with the bubble point of the reservoir being exceeded, which is known from an independent source. But there's a great deal more we can tell about the reservoir, where the stress fields are changing on the rocks versus where the pore pressure is being drawn down and where the bubble point has been reached. There's a lot of good, useful information that can come out of this level or this kind of analysis. It is worth noting that the methodology that we describe here of DAS recording applies to both 2D and 3D. So far we've seen only two-dimensional imaging, which is what I've shown you. And so we have on the screen right now are sketches of two map views of data acquisition scenarios. On the left-hand side, we see the scenario that we've discussed so far, which is a two-dimensional recording. We have our DAS cable and the red dashes as a projection of the cable at depth being projected to the surface of the Earth. And then the black dashes are indicate surface seismic sources. The sketch on the right shows, again, the red dashes being the projection of the DAS cable's position to the surface of the Earth, and then that two-dimensional grid of black dashes would indicate a 3D or a 3D seismic survey, so a two-dimensional grid of sources. In general, the three-dimensional image that we get is limited in terms of its size. It's typically only a couple of 100 feet either side of the DAS cable, the horizontal well. That said, it's very detailed because of the small receiver spacing that we can obtain from the DAS cable. So it's a very detailed image, a few hundred feet, a couple hundred feet either side of the DAS cable. And we do see fractures that cross these images typically. And so it can be quite useful information if that's what is needed in order to really investigate how the production is going in the reservoir. So the concept here is for using this technology as a reservoir management tool is shown here as a sketch of an oil field looking down onto the trace of a horizontal wellbore, where the red dash is once again is the wellbore position projected onto the surface. And in this case, we show little blue dots as seismic source points, for example, if we were doing a 3D seismic survey, 3D DAS seismic survey. And with repeated seismic acquisition surveys, we should be able to then see where changes in the reservoir are occurring, changes in pore pressure, changes in stress are occurring as a function of time, and then help the reservoir engineer determine where things are changing in the reservoir, where they're not, and therefore where they're likely producing oil and where they're not. It is worth noting that if the DAS cable is on the outside of casing, then all of the seismic operation can be done without interfering with production at all. And that's a worthwhile thing to do. And also worth noting, if you're just going to do a 2D survey, for example, just run the Vibe a 2D line right over the top of the Wellbore, that's a one-day operation. A 3D survey would be probably more like a 2-day operation, not a great deal more expensive. Continuing our reservoir management scenario, we have well 1, which is a well that's been produced for a while with some zones of pressure drawdown, say in the blue and yellow regions. And in this case, we're looking at well 2, which is now a child well offset from well 1. And we know from experience, and we know from microseismic, we know from theory and modeling that if we frack a new well next to a well where there's reduced pore pressure zones, that a lot of that frack energy is going to go right from the frack well right over to, or from the treatment well straight over to the low pressure zone. That's the waste of a lot of frack dollars. And so in a case like this, if we knew, for example, where the reduced pore pressure zones were, we might design the fracks in well 2 differently depending on how much pore pressure drawdown there was in the adjacent wellbore. And again, this is the concept we would like to promote for doing better entire reservoir management rather than just looking at a single well, looking at the entire reservoir, and it's optimizing the production and optimizing the operations in that entire field. So let's review the main points of the discussion. First, DAS data with virtual source methods takes advantage of the power of CDP velocity analysis, stacking, and migration that we have in surface seismic data to image both above and below the horizontal DAS cable. We didn't mention this during the discussion, but in fact we can see above the DAS cable just as well as we can below the DAS cable using the same virtual source technology. The second point is that time-lapse DAS imaging directly measures production-induced VP and VS changes. And that leads us to the next point, which is that rock mechanics analysis of those VP and VS changes can be used to estimate changes in pore pressure and stress above, within, and below the reservoir and lateral to the producing well. And then finally, the time-lapse seismic/rock mechanics analysis can be used to make better reservoir development decisions by knowing the pore pressure and stress state of the reservoir, the surrounding rocks, as a function of time and production. Thank you for listening today. If you'd like to learn more about this technology or other technologies at Sterling Seismic and Reservoir Services, have a look at our website at sterlingseismic.com. You're also welcome to call the office in the United States at 303-347-9011, or you're also welcome to contact me directly via email, bfuller@sterlingseismic.com. Thank you again.